Hello everyone, welcome to Wings of Physics. Myself, Deepali Kulkarni from PVP Junior College, Pravaranagar, Loni. We will continue our chapter Thermodynamics and today's lecture is lecture number 10. In this lecture, we will study adiabatic process in detail, cyclic process and the free expansion. Okay, let us start. First, adiabatic process. Adiabatic process. What is adiabatic process? Adiabatic process is a process in which no heat enters or leaves through the system. Means Q that is equal to 0 for that process. This is ideal process. It is imaginary process and it is very fast process. And for this condition means no heat enters or leaves through the system, and therefore during that process the boundary of the system that should be insulating so that no heat enters or leaves through the system. Means first condition for adiabatic process is that the boundary of this system that should be perfectly insulating, and second condition, this process should be very fast so that the system does not get time to exchange the heat with the surrounding or environment. And so for adiabatic process we have to follow the two conditions. Boundary should be perfectly insulating and the change in the system that should occur very rapidly or very fast. These are the two conditions for adiabatic process. Okay. Now consider a system. In that system ideal gas is there. Then that system is fitted with movable, massless, frictionless piston. Then first case, when adiabatic expansion is there. When adiabatic expansion is there, then when expansion is there, we know that work done by the gas. Work done is positive and internal energy is negative. Okay. According to first law of thermodynamics, Q that is equal to delta U plus W. Means if Q that is equal to 0, then delta U plus W that is equal to 0, and that is nothing but W that is equal to minus delta U. Means in case of adiabatic process, when work done is positive, internal energy is negative, or when work done is negative, internal energy is positive. Means there is a opposition in between work done and change in internal energy. And when adiabatic expansion is there, work done is positive, change in internal energy is negative. And we know that when expansion is there, gas cools down. Gas cools down means initial temperature that should be greater than the final temperature. This is the condition for adiabatic expansion. Okay, and we can say that when adiabatic expansion is there, work done by the gas. Then adiabatic compression is there. Then adiabatic compression is there, work done on the gas. At that time work done is negative. Internal change in internal energy is positive and gas warms up or gas heated. Then initial temperature that should be less than the final temperature. This is the condition. Okay. This is adiabatic expansion and this is adiabatic compression. We have to use these two conditions later on. Okay. Now we have to study the thermodynamics of an adiabatic process. Then for that purpose, we know that change in internal energy, that is always given by formula NCV dt. This is the formula for change in internal energy. And now we have to find out the work done in this process. Okay. Now we will see what is the work done in this process. Formula for work done. Work done, that is equal to integration within the limit Vi to Vf P into delta V. This is the formula for work done. Then what is the equation of state for adiabatic process? PV raised to gamma, that is equal to constant, and this constant is considered as a C. This is the equation of state for the adiabatic process. And suppose this is initial state of the system, then Pi Vi, this is the initial pressure and initial volume of the system, and it turns into the PF-VF, that is the final pressure and final volume of the system. Now for this case, we can write equation of state, that is Pi-Vi raised to gamma, and in this case we can write PF-VF raised to gamma, and that is equal to constant. This is the equation of state. This is equation of state for initial state, and this is equation of state for final state. Then what is the gamma? Gamma, that is nothing but the ratio of two specific heats. Cp is specific heat of a gas at constant pressure, and Cv is the specific heat of a gas at constant volume. It is also called as adiabatic ratio. Then gamma for monoatomic gas. What are the monoatomic gas? Helium, neon, argon, krypton, xenon, or all the monoatomic gas. Then gamma for monoatomic gas, that is 5/3. If we calculate this value, that is nothing but 1.666. Approximately we can write 1.67. This is for monoatomic gas, means gamma, value of gamma for monoatomic gas. Then value of gamma for diatomic gas. Air, that is a mixture of diatomic gas, and gamma for diatomic gas, that is oxygen, hydrogen, nitrogen, all are the diatomic gas, and gamma for diatomic gas, that is 7/5. Its value is 1.33. Okay, this is for diatomic gas, and air is a diatomic gas, and gamma for air, that is nothing but 1.4. 7/5, that is the calculation is 1.4, and the gamma for diatomic gas, that is the 1.4. Gamma for air, that is also 1.4, and gamma for polyatomic gas, CO2, SO3, all are the polyatomic gas. Then its value is 8/6, that is nothing but 4/3, and that is equal to 1.28. This is for polyatomic gas. Understood? And this is all about the gamma. Means gamma is greater, value of gamma is greater for monoatomic gas. Okay. Now we have to continue the thermodynamics thermodynamics for adiabatic process. Okay. Then if PV raised to gamma that is equal to C, therefore value of this P that is equal to C divided by V raised to gamma. Now we have to substitute value of this P that is equal to C divided by V raised to gamma. Integration within the limit Vi to Vf, C divided by V raised to gamma into dV, and that is nothing but integration of Vi to Vf, then C into V raised to minus gamma into dV. If this C is constant, then it is taken outside the integration sign, Vi to Vf. Okay. Then V raised to minus gamma into dV. We know the formula, integration of x raised to n into dx that is equal to x raised to n plus 1 divided by n plus 1. But here V raised to minus gamma into dV is there. Then integration is V raised to minus gamma plus 1 divided by minus gamma plus 1, and we can write this 1 minus gamma here. 1 minus gamma, and therefore W that is equal to C V raised to minus gamma plus 1 divided by 1 minus gamma, and limit of integration is Vf and Vi. Then work done that is equal to C divided by 1 minus gamma, then Vf raised to minus gamma plus 1 minus Vi raised to minus gamma plus 1. Okay. We can write this step in this manner. W that is equal to C divided by 1 minus gamma 1 by Vf raised to the gamma minus 1 minus 1 by Vi raised to gamma minus 1. If this C is taken inside, we can write here C. Then value of C, when final state is there, equation of state is Pf Vf raised to gamma, and when initial state is there, Pi Vi raised to gamma that is equal to C. Now we have to substitute value of C, Pf Vf raised to gamma. Okay, and here Pi Vi raised to gamma. Then it becomes this gamma that gets cancelled. Vf raised to minus 1 that is nothing but Vf raised to 1 plus 1, and it becomes the Pf Vf minus Pi Vi divided by 1 minus gamma. This is the work done in case of a adiabatic process. Now we have to write this equation in terms of the temperature. We know that PV that is equal to nRT, and therefore nR is taken as common. Inside bracket we have to write Tf minus Ti, but we write here Ti minus Tf divided by 1 minus gamma, means this is the work done in case of a variables nRT, because we consider this case that is adiabatic expansion, and for adiabatic expansion work done is positive and Ti should be greater than Tf, and therefore we have to write instead of Tf minus Ti, here we have to write Ti minus Tf. Okay. If the adiabatic compression is there, then we have to write work done that is equal to nR Tf minus Ti divided by 1 minus gamma, because the adiabatic compression is there, work done is negative. Okay, and therefore this is the formula for adiabatic expansion. Work done is positive, and this is the formula for adiabatic compression when work done is negative. Understood? Then adiabatic process, that is also called as isentropic process, because entropy of the system that remains the same in case of adiabatic process, and therefore iso means same, entropy of the system is same, and therefore it is called as isentropic process. Adiabatic process is also called as isentropic process. Okay. Now we have to study the PV diagram for this adiabatic process. The PV diagram for adiabatic process. PV diagram. Then pressure is here, volume is here. Then this is the nature of the PV diagram. Now in this case, Pi is the initial pressure, Pf that is the final pressure, Vi is the initial volume, Vf that is the final volume. This nature is rectangular hyperbola. Then the PV curve for isothermal, this red curve, that is the PV curve for isothermal change or isothermal process. Though nature of both the curve, that is the rectangular hyperbola, but this is the more steeper. Means what is the meaning of more steeper? Means slope. Slope for adiabatic process, slope for adiabatic process, that is minus gamma into dP by dV. And slope for isothermal process, that is dP by dV. Okay. Then if we consider the magnitude, then slope of adiabatic process is gamma times greater than the isothermal process. And just now we studied the gamma, that is large for monoatomic gas, and slope in case of a adiabatic process, that is very large in case of a monoatomic gas. And this is all about adiabatic process. Puncturing of a inflated balloon, puncturing of a tire, all are the examples of a adiabatic process. I hope all of you understood all this process very well. Okay. Now we will study the cyclic process. Next process is cyclic process. Cyclic process. Cyclic process. What is the cyclic process? Cycle. Name in itself indicates that a cycle is there. Suppose initial state and final state. Initial state and final state of the system, that is same. Means a system returns to its initial state, though some changes are in the system are there, but the initial state and final state of the system, that is same. Suppose P1 V1 is the initial state, and again P1 V1, that is the final state. Means initial state and final state of the system is same, then we can say that the process is a cyclic process. Okay. Then this is the PV diagram for the cyclic process. Okay. Now what is the value of work done? Work done, that is equal to the area under the curve, means in this the shaded area, that gives you the work done in case of a cyclic process. Then we already studied that the heat and work, they are the path function. They depends on the path. But internal change in internal energy, that is a state function, and it depends upon the state. Means if initial state and final state of the system that remains same, then change in internal energy of the system that is always equal to 0 in case of a cyclic process. Then according to the first law of thermodynamics, Q that is equal to delta U plus W. If delta U that is equal to 0, Q that is equal to W. Means heat supplied to the system is used to perform work done, and area under the cycle that gives you the value of work done. Suppose this is the case. A cycle is there. System starts from point A and this cycle is in clockwise direction. Then the shaded area means area of this circle that gives you the value of work done, but this work done is always positive. Means a cycle is in clockwise sense, then work done is always positive. This is the sign convention. And again same circle is there. The system starts from point A and returns to point again at point A, but it is in anti-clockwise direction. Though value of work done is the same, but work done is the negative. Work done is negative. Okay? Means if cycle is in clockwise sense, then work done is positive. Cycle is in anti-clockwise sense, work done is the negative. And working of all heat engines that is based on the cyclic process. This is all about the cyclic process. In case of isothermal change also, Q that is equal to W and change in internal energy is 0. In case of a isothermal change, that is same, but there is some difference. A change which occurs at constant temperature, that change is called as isothermal change, and when a system return to its initial state again and again, that process is called as cyclic process. This is the difference between isothermal change and cyclic change. And the last process of this chapter, that is the free expansion. Free expansion. Free expansion. I already explained the free expansion in very detail in lecture number 7. What is the free expansion? The puncturing of a inflated balloon, puncturing of a tire, that is the best example of a free expansion. And in case of free expansion, Q that is equal to 0 and W that is equal to 0. Means no heat enters or leaves through the system, and work done also in that case is 0, because expansion in vacuum, that is called as free expansion, and therefore there is no necessity of work done. And again we know that Q that is equal to delta U plus W according to the first law of thermodynamics. If Q that is equal to 0, W that is equal to 0, then delta U that is also equal to 0. Means all these three things, the heat supplied to the system is 0, work done is 0, and change in internal energy is 0 in case of a free expansion. Then the free expansion, it is a uncontrolled change. Again it is instantaneous change, it is very fast change, and so that the thermodynamic system does not remains in thermodynamic equilibrium. Means thermodynamic equilibrium, that cannot be, condition of thermodynamic equilibrium cannot be obeyed in case of a free expansion, and it is a very fast process, so that we cannot plot a PV diagram for free expansion. Okay, only initial state and final state of the system we can plot on the PV diagram. Okay, and this is all about the free expansion. Here all the process in thermodynamics are over. Okay, in next lecture we have to study about the heat engines. I hope all of you understood all these process very well. If you like my video, then like, share and subscribe my channel. Okay, thank you very much.